Hello, everybody. In this lecture, we consider convolutions. So last time, at the end of the last lecture, I have done a small calculation about convolution for smooth functions, and that calculation suggests that a convolution should be defined as the tensor product of two distributions applied to a certain transform of the test function, and this transform maps a function of one variable to a function of two variables through this relation in here. So phi delta of x and y is defined to be phi of x plus y, okay? And phi is taken to be a test function. And as I mentioned last time, this phi function, test function is test function, does not imply the phi delta function is a test function. In particular, we can find examples for which the support of phi delta is unbounded. So typically, the right-hand side in here is not well defined because T tensor S is a distribution which defines only for test functions. I mean, C infinity function with compact support. So if the support is unbounded, we cannot make sense of the right-hand side. So the goal of the following is to make some assumption on the distribution. In particular, make some assumption on the support of the distribution T and S, so that we can still make sense of the right hand side. So our agenda is the following. So the first thing we're going to do is to define enlarge the space of test functions in view of the support of the distribution. So we can imagine that if the support of this guy is super small, like a Dirac mass. If that is the case, then we do not care about the behavior of the test function at infinity. So in particular, we can make sense of this bracket, even though phi could be not vanishing at all at infinity. So this is the basic idea. We are going to enlarge the space of test functions according to the support of T and S. And then we can extend our tensor product Ts to this enlarged test function space. And this will be denoted by T tensor S tilde. And eventually we're going to show that this phi delta thing that which is defined in this way belongs to the enlarged space, so that this guy, this extension of the T tensor S, can be applied to this phi delta function. And this time, this guy will be making sense. Okay, so let's do this one by one. The first thing I'm going to do is to introduce the enlarged space of test functions. And this is the content of definition 10.1. First, we consider F a closed subset of Rd. Then we define the enlarged space of test functions denoted by calligraphic E of F omega. So this depends on two things. This depends both on the closed set F and on omega, on which we define our test function and distributions. Okay. So this is given by the family of C infinity functions on omega, okay, such that the support of phi intersecting F is compact. So first observation is that if this space of test functions is larger than the space of test, this enlarged space is indeed larger than test function space because this function may not have a compact support. All we need is that its support intersecting F is compact. Okay, so we have a larger space. So the important observation is the following. It says that we can extend our any distribution to this new defined space where F is taken to be the support of T. Okay, so we take a distribution on omega, then T can be extended uniquely to a continuous linear form on this enlarged space of test functions. Note that this F is taken to be the support of T. Okay, so T can be extended to a larger space, which has something to do with its own support. So by this actually means that we can find the linear form T tilde on this space, this larger space, such that T tilde coincides with T on the space of test functions, okay, on the classical space D space. And also, if we have a sequence phi j C infinity such that its support intersecting the support of T is contained in a common compact subset of omega, and also satisfy that all the partial derivatives converges uniformly to the partial derivatives of phi, then we have this continuity property. Okay, so there are two things that we want to show. We want to have an extension, meaning that it coincides with T on the space of test functions, classical space of test functions. Also has it satisfied this sort of continuity property. Okay, so let's do this one by one. Proposition 10.2. So we want to first give a definition of this extension. So we consider any phi in the space, let's say enlarge the space, omega. And we consider a C infinity function chi omega such that the product of this function with chi, product of chi and the test function phi, enlarge the test function phi, has compact support. Okay, C infinity is compact support. And also, we require that this guy is equal to 1 in a neighborhood of the support of T intersecting the support of phi. Recall that this guy is contained in a compact set because of the definition of this enlarged space of test function. Okay, so this guy equals to 1 in the neighborhood of this compact set. And of course, we can take chi to be the cutoff functions. In other words, chi has also compact support, but this is not necessary. All that I require is that the product of these two functions is in the space of test functions, and also it equals to 1 in the neighborhood of the intersection of support of T and the support of phi. Okay, this is the region which matters for the distribution for T. Okay, once we have this, we can define as follows. This T tilde applied to phi will be defined by T applied to chi phi. Okay, so since we have this requirement that the product is a test function, this right-hand side is well defined. So at least this guy is a finite number. Okay, so in order to say that this whole thing is well defined, we still need to check that this guy, the right-hand side, does not depend on the choice of chi. Otherwise, it's not a good definition. So first thing we're going to show is that we show that the choice doesn't matter. Choice of chi does not matter. So in other words, if for phi 1, okay, chi 1 and chi 2 both satisfy the property, the properties that I mentioned, then if we take the difference of these two, I should find 0. Okay, and this is true because this will be 0 since for the simple reason that the support of this function, the product, will be obviously included in the support of chi 1 minus chi 2 intersecting the support of phi. And we know that this function chi1, chi2 both equals to 1 on this set. Okay, so that on this set, the function coincide. So the supported function will be intersecting the spot of phi will be empty set. Hence, this value has to be 0. Okay. Okay, this value has to be 0 because, okay, so let me just write it more carefully. So all what we know is that this kind of bracket will be 0 if the support of T intersecting the support of this guy will be empty. But we have already shown that, so this implies that the support of T intersecting the support of chi1 minus chi2 phi is empty, so that we have 0. Okay, that's it. So this is only the first step. So then the next step will be to show that this is a linear form. Okay, so this is a linear form. So let's do this. We are going to show this linearity. To show that, we consider phi 1 and phi 2, which both are taken from this enlarged space of test functions, T omega. Then we consider chi C infinity such that this chi phi is a test function. Okay, so there are two functions. So let me say both this guy and this guy are test functions. We can do that. As I said, we can just take a cutoff function such that this is equal to 1 on the support of T intersecting the support of phi 1 union the support of phi 2. So we know that this is actually the intersection of two compact sets because this intersection of support of T with support of phi 1 is a compact set by this assumption. Likewise for the phi 2, so intersection of two compact set is a compact set. So this kind of function we can find it by, for instance, taking the cutoff function. So now we can compute this T tilde applied to phi 1 plus phi 2. Okay, and first of all, by the definition, it becomes chi times phi 1 plus phi 2. And by our choice, we know that this guy satisfies the property that it is a test function, and it is equal to 1 on this set, right? So by the it is equal to 1 on the set. The support of it is equal to 1 on the support of T intersecting the support of this guy, and the support of this guy is included in the support of it's included in the support of phi 1 union the support of phi 2. So we do have this property. Okay, so once this is done, okay, so we're all good. We can separate these two terms, then use the definition again to have the linearity. Okay, so now it remains to show this continuity. So continuity. So for that, we are going to consider a sequence of functions in the space, enlarged space of test functions, such that, okay, so according to this the requirement, the second requirement, we need to check this property for this sequence. Right? So the sequence satisfies the property that the support that has a intersecting the support of T is included in a common compact subset of omega, and also we want to show that this the partial alpha pi phi j converge uniformly to partial alpha phi for all the alpha. And so let's do this. We want to show this property. We want to compute this property, and also we want to show that this guy converges to the right hand side in here, right? So first of all, we can, okay, let me just introduce another function. So let me introduce a function, chi. Okay, so this is the sequence. So I haven't said that this sequence satisfies this property uniformly for all alpha and d. Okay, so now we consider a chi be let's just take it as the test function d omega, such that chi is equal to 1 in the neighborhood of the support of t intersecting k. Okay, so this k is the common support of this sequence of function, and this is a compact set by assumption. So we can compute t tilde phi j as t chi phi j. Okay, so this we have this formula because of our choice of chi and the definition, and then this guy converges to t chi phi, which is nothing but t tilde phi. So this is exactly what we want to show. But this convergence is guaranteed by the fact that this guy converges to this guy in the space of test functions. So because just one thing, phi j minus phi, so this guy, if we take the partial alpha, this guy will converge uniformly to 0 for any alpha. Okay, so they have a common support. This guy has a common support, which is k, because which is this guy. Right? On the one hand, it has common support. On the other hand, they have this uniform convergence by assumption, so that we do have the convergence of this sequence towards this product, which finished the continuity part of the proof. Okay. Now that we have extended distribution to a larger space, and we want to know actually how large this space is. So there are two extreme cases. Let me just consider the first case is when we take F to be the whole set, to be the whole RD. And in that case, so let's look at the definition. It says that this phi is C infinity such that the support of phi intersecting RD is compact, which means that the support of phi is compact. In that case, this set is not really larger than the space, the classical space of test functions. Okay, so this enlarged space is equal to the classical space of test functions. So, but on the other hand, if we take, for instance, the support of T is a compact set, okay, in that case, this space is really larger, much larger, because if F is a compact set, then this is necessarily a compact set because this guy the support of phi is a closed set. Okay, intersecting compact set is still a compact set. So we have capacity for the support of T. Then necessarily this set, this enlarged space, is much larger. Let's get back to this this formula for a moment. So as I said, this guy may not have a compact support. This phi delta thing may not have a compact support, but it is clearly a C infinity function because phi is a C infinity function. If the support of T tensor S is included in a compact set, then this guy, there's no problem in defining such a quantity. Okay, let's look at the original problem, right? So we don't have a problem in defining such quantity if this guy has a compact support. So this is a basic idea, and we're going to see what we can do with the support of T intersection, the T tensor product S, and what kind of assumption we should put on this tensor product or on T and S such that this guy is well defined. Okay, so in order to do that, let me introduce a few more definitions. The first thing I want to introduce is All right. First thing I want to introduce is the notion of convolvable closed sets, right? So let's consider F and G closed sets, closed subset of RD. So say the pair FG is convolvable if for any K compact subset of RD, I consider the inverse of this S map. S is the sum of X plus Y. S is defined on R2D. Okay, it's a function of two variables. So this is a typo. This should be X plus Y. So we consider the inverse of S of a compact set if the inverse of S of a compact set intersecting F times G, this is a product of the two sets. So this is a rectangle. This intersection is a compact. Then we say F and G is convolvable. A pair of distribution T and S is convolvable if the support of T and the support of S, this pair is convolvable, right? So this is our definition of convolvable, and it turns out that convolvable distributions, we can compute a convolution of convolvable distributions. Okay, that will be proposition 10.5. But before that, let me just check one thing. Let me check that this phi delta belongs to the space of enlarged space of test functions, as I already said in the agenda. We want to show that this guy, if T and S are convolvable, okay, satisfy this property that I just said in definition 10.3, then phi delta belongs to the enlarged space of test functions with F equals to the support of T tensor S omega. Okay, so let's do this verification. 10.3, 10.4. Okay, so first of all, this guy of a two variable, since it is equal to phi of X plus Y, it is C infinity omega times omega, okay, on the product space. Also, the support of phi delta intersecting the support of T tensor S is equal to S inverse. Recall that S is the sum of the two components. So S inverse of the support of phi, okay, this is by the definition of this phi delta, intersecting the support of T times the support of S. This is what we know from last time. So support of tensor product is equal to the product of the supports. So this is what we have. So now, according to the definition of convolvability, so T and S are convolvable so that this guy is satisfied. This property is satisfied. So that this guy is a compact set because T and S are convolvable. Okay, so this is done. We're done with it. So this is a compact set. This is exactly what we want to show for phi delta to belong to the extended space of test functions. Okay, so now finally we can give a proper definition. So we are going to define the convolution as this. So define the convolution as okay, as this formula, and we want to show that this guy is as a linear form of phi test function is a distribution. Okay, we already showed that this guy is finite by showing this lemma 10.4, right? Phi delta belongs to the enlarged space of test functions, so that this guy is well defined, and this guy is finite. So it remains to show that this is a linear form on the space of test functions as a linear form of phi. So let's do this. Proposition 10.5. Okay. So there are two things. So the first, we're going to show linearity. This part is easy because let phi 1, phi 2 be test functions, then it is immediate to see that if we take the delta of the sum, this will be equal to sum of the deltas. Okay, so that when we apply the convolution to phi 1 plus phi 2, we can separate these two terms, right? So let me just write it out. So T as applied to phi 1 plus phi 2, which is according to definition tensor product tilde phi 1 plus phi 2 delta. Okay, since we have this property, we can separate these two terms. So we're going to have this plus the same thing applied to phi 2 delta, and this is nothing but T tensor S phi 1 plus T tensor S phi 2. Sorry, convolution, not tensor. Convolution of T and S, convolution of T and S. Okay, so this is the linearity part. So then we want to show also the continuity. For that, let's consider phi j converges to 0 in d omega. Okay, so it's a sequence of test function converging to 0, and we're going to show that T convolution of T and S applied to phi j converges to 0. This is the goal, right? Then we have that. Okay. Then, so we want to show that T tensor S phi j, which is equal to T convolve with S, applied to phi j. Then it is equal to T tensor S. This time it's tensor S tilde phi j delta. So in order to show that the right-hand side goes to 0, since we have already shown the continuity of this guy, it suffices to show that this guy goes to 0 as a function of two variables, actually 2D variables. Okay, so it remains to show that the partials, this guy, this alpha, let's say alpha 1x, alpha partial alpha 2y, two variables, phi j delta is a function of two variables, x of y. Okay, here it is. So we're interested in this quantity for all the alpha 1, alpha 2, and then we compute a uniform norm and let j goes to infinity. So this guy can be written differently because this is phi x alpha 1, dy alpha 2, phi j of x plus y, okay? And this is nothing but phi alpha 1 plus alpha 2 this time. Then phi j x plus y. Okay, so it's first to take the partials for the phi j function, then evaluate it at the point x plus y. This is what we have. And if we take uniform norm now, using the fact that this function phi j goes to 0, we see that this guy goes to 0. And this guy goes to 0 means that we have this convergence. And this finish the continuity part. Okay. Now that we have a definition, so we would like to consider a few examples. Okay, few examples, and first one will be L1 log function. So example 10.6. Okay, so L1 log example. So we consider two L1 log function f and g. Assume that they are convolvable. Then we argue that the convolution of these two distributions associated with the L1 log function, TF, TG, the convolution of them is given by T associated with the convolution in the classical sense, right? So this function. And we claim that this function given by this formula is also L1 log function, and so that this right-hand side makes sense, right? So this T associated with L1 log function. Okay, so let's first see why this function, this formula given here is L1 log. Okay, so to show that, we just do the integration on a compact set. Let K be a compact subset of omega, and then we compute integral on K of this formula, x minus y, g of y, dy, and we want to show that this guy is bounded, and it is clearly bounded by. So if we take the we can take the absolute value inside in here, and then we write this integral on K as integral on RD times the indicator on K of the x variable. So all that is to claim that this indicator on K of the x variable, then f of x minus y, g of y. So this guy, this double integral, gives the upper bound for the thing we want to bound. Now, so we can make a variable change, and we're going to see that this eventually becomes x plus z, x plus y, f of, this is the new x, variable change, and g of y. All right, that's it. According to this definition that f and g are convolvable, we know that this support of this guy must be compact. This guy has compact support. Okay, because we have a convolvability between of the support of f and the support of g, which means that if I take S inverse of this k, I get back the vector xy. Okay, so I know that xy belongs to k, so the support, compact support, because let me just write it out explicitly, the support will be given by this. and according to the definition, the assumption that f and g are convolvable, this guy is compact. So we're all good. This means that it's finite, which shows that f convoluted with g, this symbol in here, given by this definition, the classical one. This guy is L1 log. As long as both functions f and g are L1 log and that f and g are convolvable, okay, there are two conditions, then we have the convolution in the classical sense is also L1 log. Okay, so now we want to show the formula, but that part is easy. So TF, TG applied to a test function. So let's see what it gives. So first, we know that this is the, according to the definition, this is the tensor product of f and g, which is given by the Euro tensor product f and g. And then we extend it and apply it to phi delta. Okay, this is what we have. And we know that this function f tensor product is just this guy, fx times g of y. Integral applied to this phi of x plus y. And also there's a chi function because we have an extension. This is defined to be this guy applied to that times a chi. So we got a chi function xy, which equals to 1, where chi is just a C infinity function such that this chi is equal to 1 on the set that the support of f times the support of g intersecting the inverse of the support of phi in here is compact. Is equal to 1. Okay, so this is equal to 1, and this is indeed a compact set. Yes, this is indeed a compact set by the assumption f and g are convolvable. Since this is the case, this is equal to 1. In this integral we can just remove it because this is precisely the support of the two of the function of this function of two variables. Let me just double integral. Okay, so we can actually remove it because it's equal to 1 on the support, and then we continue. We can put things together by using Fubini, and we see that we got this f x minus y gy thing, dy, and this is precisely the formula of g of x. On the other hand, times the phi of x dx, and this gives the formula f convolution with g time applied to phi. Okay, so this gives the formula. Okay, our second example is about a convolution of a distribution with a C infinity function. Okay, so as always, we assume that the support these two distributions T and F is a convolvable pair. Then we are going to show that this T convoluted with F is a C infinity function, and it takes the particular form as such. Okay, so convolution of any distribution with a C infinity function becomes automatically a C infinity function. A very important fact. Okay, so let's show this fact. So first of all, we consider T convoluted with F applied to phi, and according to the definition, this is nothing but the tensor product of the two distribution applied, so there's a tilde applied to phi delta, okay, the extended version of that. So we can find a function chi such that we have this formula. Okay, just Euro tensor product applied to a test function. So now we can make use of a formula for the tensor product. That's sort of a Fubini theorem, so Fubini type theorem for tensor product. We can first apply this f to the we can apply f to the y variable of this test function, then apply t to what we got for this function of x variable, or we can first apply t to the x variable of this function of two variables, then apply f. So it's kind of Fubini kind of argument. So this time we're going to use the part where we apply first t, then f. So it's going to be f applied to t applied to something. And this t applied to something, let me just write it explicitly. Tx on the x variable, so I write tx to indicate this fact. And there inside, I'm going to have this chi function x, y, and also phi of x plus y. Okay, this is the definition of phi delta. There it is. And the whole thing dy. Okay, so this is a formula that we have shown already last time for tensor product. So now we can make use of an important fact, which says that so this is the integral. This is sort of a Fubini theorem, right? So the integral will interchange the order of integral and the bracket. So again, something that we have shown already: f of y, chi of x, y, phi of x plus y, dy. All right. So the trick is now to make a variable change. So let's pass the dependence on this x variable, or let's pass the x variable all to the function f and the chi, so that I can separate this phi with the others in order to have a formula of the type a distribution applied to phi. Okay, so this change of variable, let me just call x plus y z, so that it becomes the integral of f of z minus x, chi of x z minus x, okay, and phi of z, dz. And that's it. All right. So we apply again, interchanging the order of integration and the bracket. So we're going to have integral then tx f of z minus x chi x z minus x. Okay, then pull it out, dz. Finally. So this is exactly what we want to have, right? So this we have a formula. This is a distribution. It's a function of z variable times phi. We do the integral, so this means that this shows that t convoluted with f as a function of z takes this formula, takes this form. T, okay, I can forget about x because there will be no more x. So f z minus the variable, so t act on this variable, chi of variable dot z minus variable. Okay, so this is our formula, a function of z, which shows that we indeed have a function. So we haven't shown that this guy, we haven't shown that this guy is given by that formula that we want, but we're pretty close. Okay, so this actually, we can just write one more step. So this will be t tilde f of z minus the variable, if we can show that this guy for any z fix, this guy is C infinity on the dot variable, and it takes the value 1 on the intersection of the support of t and the support of fz minus variable. Okay, and this is this we can show. This we can show because of the assumption of this chi in here. This chi satisfies the property that it is equal to 1 on the intersection of the it is equal to 1 on the intersection of the support of t times support of f with the support of phi. Okay, so combining these two things, we can show exactly that, which means that we do have this formula, it's a T extension times F Z. This is exactly what we wanted to show. And the last property that this T convoluted with F is C infinity is automatic because now we notice this guy takes this form, and by using differentiation under the bracket, we see that this guy is indeed a C infinity. So so long as this guy is C infinity is compact support, which is the case, we have this guy also C infinity. Okay, that's it. That's it for the example. Okay, so next page. So we have equivalent definition or another formula for the tensor for the convolution. Let's see how we can do this. It's proposition 10 point. Next page. Proposition 10.7. So we consider a convolvable pair, then we give another formula for that convolution. So we have shown that this convolution is related to the tensor product, but we can also write it differently because tensor product also have a different form, right? So we can apply the Fubini type argument. So this is exactly that. So one more step beyond our convolution, beyond our tensor product expression for the convolution. So let's show this. So first we consider any test function, and we consider a C infinity function. So we can just take a C infinity with compact support, which is equal to 1 on the compact set. On the compact set given by all those x in the support of T, okay, such that there exists a y in the support of S with the property that x plus y belongs to the support of phi. Okay, so of course another way to write it or write the same thing is to do the projection to the first variable of S inverse of support of phi. Okay, this is precisely this. So the sum of this sum of a point in the support of T plus the point in the support of S belongs to that, and we consider only those x. So we do the projection. So first we have a point set in the product space, and then we do the projection to the first variable. We obtain exactly this one. And since this is a compact set according to the okay, so I forgot one thing. Intersecting support of T times support of S there. Okay, since according to the assumption T and S are convolvable, this guy is compact, and projection is a continuous map, so this guy is also compact. All right. Now we letting this chi x y. Okay, we define a function of two variables by just extend it extended the chi function to the product space. And this function will not be having a compact support because it takes the value 1 constantly because it doesn't depend on y, right? So if x is in the support of chi, then this guy is not 0, then we can vary the value of y without changing the value of chi. Okay. So the support, this guy does not have the compact support, but we don't want. But the compact support is not a necessity for defining a convolution with that tensor product formula. So all we need to verify is that this guy times this is compact. But this is clearly true by our by looking at the choice of this chi function. Okay, because the function chi here has compact support. Since it has compact support, the other one is just function of phi, which also has compact support, right? So this guy more precisely is this times phi of x plus y. So it takes so the first variable will be non-zero, okay? But all the x in the support of chi, it is non-zero. Outside of it, it becomes 0. On the other hand, for all the y, since this is constrained to a compact set, x is included in a ball of size r, say, and then y plus x being inside the support of phi has a restriction to the value of y. So y will also be included in the large set, so that the support of this guy is actually contained in the big ball, right? Which means that the support is compact, right? It's bonded. So support is always closed with bondedness. We have a compact set. Okay, so this property is satisfied, and this that's enough to define a tensor product extension. So T convolved with S applied to phi, and then we know that this is T tensor S applied to chi phi delta there. Okay, so now we're good because we can apply our formula for the tensor product. We know this Fubini type formula for the tensor product. We can apply S to the second variable, which is chi does not depend on the second variable. We just pull it out, and S applied to the second variable y of this function phi delta, and this is what we got. So this guy is by definition C infinity with compact support taking value 1 on this compact set, right? So in particular, it is it takes the value 1 on the intersection of support of T with the support of this function. Okay, so this becomes T tilde applied to this function. Here. Okay, so Tx. All right. And this is precisely what we would like to show in this formula. This is T tilde applied to psi with psi equals to this function that we have proved. Okay, so next thing, for the rest of the lecture, I'm going to show a bunch of basic properties about convolutions. And the first thing is commutativity. We know already that tensor product, we cannot commute tensor product. Okay, so there are typical examples. But convolution we can commute. So let's show this. 10.8, commutativity. So first remark is that by using this property, with this exactly the same proof of this one, we can have a similar formula of the type S tilde applied to another function, which is T applied to the first variable of chi phi delta. Okay, so that's the another formula with the same proof. Of that of proposition 10.7, we can show by using a Fubini type of argument, because there are two formulas for the tensor product, We have already used one of them to derive proposition 10.7. We can use another one to derive another formula. And that another formula would be this guy, the formula I'm going to write down. T convolved with S applied to phi is Sy applied to chi of y Tx phi of x plus y. Yes. Okay. So we first this time we first apply t to the x variable of chi times phi delta. Then we apply s to the obtained function in here. Okay. So that according to this formula, but we use this formula now, but backwards. So we're going to have s t phi. And this finished the commutativity proof. Okay, so now let's verify a simple fact, which is that t delta 0 is, so we can commute, right? These two guys we can commute. So delta convolved with t is equal to t convolved with delta. And the point is that this delta thing is actually unit element for tensor products of distributions. It's like a 1 in the regular multiplication. Okay, it's a unit element. So this guy is equal to t. So let's do the verification, and we already have a formula for this kind of convolution. So we just use this formula 10.7 that we obtained. So that one gives us a t applied to tx applied to chi of x, then phi of x minus y, and this y equals to 0, okay? Because we applied delta function to that part, so it remains only x, okay? And this chi function equals to 1 on the support of t intersecting support of phi, so that this guy really doesn't matter. So we have this t applied to phi, which means that t convolved with delta is equal to t. Finish the proof. Okay, so next we consider derivative. So these are this is also not hard to show. 10.9. So let's just consider the derivative of the convolution applied to phi. Then first use the definition TES, then we pass the derivative to the test function with negative sign, and then we can write it as the tensor product T and S applied to a chi function that we all know how to choose. Chi j phi delta. Okay, exactly. So now notice that we can actually interchange the delta operation and the partial derivative. Let's see why. Okay, so this is the nothing but phi dj phi of x plus y. So this is it. And we can take the partial derivative with respect to xj of this function phi of x plus y. Okay, take this partial derivative, we obtain the same thing. And we notice that this guy, xj, is nothing but phi delta. Okay, so we interchange this order, which means that let's continue the calculation. So we have this t tensor S applied to chi delta phi xj. Okay, so now we can use Leibniz rule to write it as negative t s tensor product applied to dxj of this chi function times phi delta and there will be an additional term, which is T tensor S applied to dxj chi times phi delta. Oops. Times delta. All right. So the observation is that this guy actually goes to, this guy is equal to 0. The second term is equal to 0 because this guy is equal to 0. Okay? This guy is equal to 0. Because it's a constant function on the support that matters. So the second term doesn't contribute at all. So it remains only this term, and we can pass it, the derivative, back to the tensor product, and we're going to have this djt tensor S applied to chi phi delta, which becomes, just forget about the chi function, I put a tilde in there, and which is nothing but djt convolve with S applied to phi. And it's finished. So it shows that this guy is equal to this guy, and this is what we want to show. Okay, let me try to put it. Okay, next. Next we consider support. So 10.10 says that the support of a convolution is included in the sum of the supports. Okay, this is also a classical fact when in the case of functions. This extends that proof of 10.10 support. Okay, so we are going to start with a fact. In general, the sum of two closed set, the sum of two the sum of two closed set is not necessarily closed, right? This is not true. But in the case where the two closed sets are convolvable, we can actually show that the right-hand side in here, this if these two sets are convolvable, two closed sets are convolvable, the sum will be a closed set. This is the first thing I'm going to show, which does not hold in general. Okay, so first effect, if f g convolvable, this pair is a convolvable pair, then f plus g is closed. Okay, so convolvable pair contains two things. It says that f and g are closed set, and S inverse of a compact set intersecting f times g is a compact set for any k compact. So let's do this. So proof of this fact. So let's consider, so in order to show this closeness, we consider a sequence that is convergent. And we're going to show that the limit is included in the set. So we consider Zn, which is in the set f plus g. We assume that it is a convergent sequence. Be convergent with limit that we call z. Okay, the goal is to show z belongs to f plus g. According to the definition of f plus g, we know that we know that there exists an xn in f and a yn in g such that, okay, zn f plus g. Zn is xn plus yn. Okay, this is just definition of f plus g. But also, we also know that this set as the inverse of S map of this sequence. So this is actually included in a compact set. In a compact subset of the product space. That is because Zn is a convergent sequence, so that it is bounded, right? It is bounded, so S inverse of this the sequence is contained in a S inverse of a certain compact set. And the compact set is actually the closure of the sequence. And that is included in that compact set since we already know that F and G are convolvable. We know that this guy is a compact. Okay. Because of the compactness, we can find by compactness, we can find a subsequence such that X and K converges to X. And since X and K is chosen from F and F is a closed set, we know that X belongs to F. We can deduce that this Y and K, which is nothing but Z and K minus X and K, since Z and K converges to Z and X and K converges to X, we have that it converges to Y and K converges to Z minus X. And also, Yn is chosen from a closed set G, so the limit must belong to G. In summary, we have established that Z, which is X plus Z minus X, belongs to F plus G. And that is precisely what we want to show. That's it. Okay, so from this fact, we can prove this result for the support of convolutions. So we first consider for any x which is not in the right hand side, our goal is to show that it does not belong to the support. Okay. Since the right hand side is really a compact set, it's not a compact set, but it is a closed set. We can find an R positive such that a ball centered at X with radius R intersecting this guy, this sum of the two supports, is empty. Okay, this is by closeness. Hence, for any phi test function with supporting Bxr, T convolved with S applied to phi will be Ts chi phi delta must be 0. And that is because that the support of T times the support of S, which is the support of T tensor S, intersecting the support of phi delta, we want to infer that this guy actually is empty, right? So if this is empty, then we're done. So this is nothing but S inverse of S T plus the support of S, intersecting S inverse support of phi. So S is just the sum of two maps, two variables. So S of x y is equal to x plus y. So we know that this is nothing but S inverse of the intersection of these two sets, and phi. And according to what we have shown already, according to the closeness, we know that this guy is actually empty set. So this guy's empty set, and the inverse of empty set will be empty set. And that's finished the argument. Okay. This shows that X does not belong to the support of T convolved with S, which is what we want to show. Okay, that's it. Let's move on. Next thing is about convergence. Convergent. So this is quite natural actually. So if we have a sequence of distribution that converges to T and the sequence Sn converges to S, and also there exists a convolvable pair of closed sets Fg such that the sequence Tn has support included all in the closed set F, and sequence Sn has support all included in the closed set G, then convolution of the sequence converges to the convolution of the limits. Okay, so this actually just follows from our continuity result for the tensor product, because when we define convolution we use tensor product, right? Just quick proof. So if we consider phi in any test function, and we can consider any cutoff function, omega times omega, with this property that this is equal to 1 on f times g intersecting the support of phi delta. Okay, then we can consider Tn convolved with Sn applied to phi. Okay, and this is given by Tn tensor Sn applied to chi times phi. Okay, and according to our result, the continuity result for tensor product, this converges to T tensor S applied to chi phi, which is nothing but T convolved with S applied to phi. Done. Okay, so continuity is simple. So now it remains just one thing in this lecture. So we are going to consider associativity. All right. Associativity is true in general for tensor products, but it is not necessarily true for convolutions. So there's a typical example. Let me just give the example. So if we consider t equals to 1, s equals to t is equal to 1, s equals to delta function prime, and u is the Heaviside function. We know that Heaviside function, the derivative of Heaviside function is a delta function. It's this delta Dirac mass, and the derivative. Okay, let's just do the calculation for the convolution of the first two things. So what do we have? If we do the convolution of a 1 with delta naught prime, we know that it's 1 prime delta naught according to this derivative property 10.9. Okay, we can take the derivative to either one of the distributions as much as we want. So we take the derivative instead of on delta function, we take the derivative for the constant function, which is 0. Okay, and 0 convoluted with anything will be 0. So this guy is 0. On the other hand, if we compute the convolution of delta naught with the Heaviside function, so for the same reason, we can just compute the convolution of delta with the derivative of h, which is delta. So delta is the unit element, so we obtain still delta. So which means that 1 convoluted with delta prime, then convoluted with h gives the value 0. And if we compute the convolution of delta prime with h, then convoluted with 1, we know that we have 1. Okay, because this guy gives a Dirac mass, and Dirac mass is a unit element, so the convolution will still be 1. So in other words, we don't have associativity, right? So this guy is not equal to this guy in general. So however, we have a criteria for associativity if the support of TSU satisfies certain nice properties. And by nice, I mean what we mentioned in this proposition 10.12. It says that TSU is a convolvable triple of distributions in the sense that S inverse, this time S is the sum of three variables, S inverse of any compact set intersecting the product space, the product of the spot of T, the spot of S, support of U is compact. Okay, same kind of definition, but this time for three variables. So let's do this. So first thing I want to show is to make sure that this both sides make sense, in the sense that this convolution T and S as a distribution is convolvable with the distribution U. And this is not very clear for the moment. We know so it is automatic from this property that T and S are convolvable. If three guys are convolvable, then any two of them are convolvable. But whether or not the convolution of two of them with the third one is still convolvable, that is not so clear. Okay, so first thing I'm going to show is to show this property. So for that purpose, let me introduce a bunch of maps. So there are a lot of maps. Okay, so proposition 10.12. Okay, whatever. So let me introduce a bunch of new maps. So first, S is a zero. There are three variables, and I still call it a map from R3D to RD given by this. Okay, so this is the map that I have already introduced. I introduced this map T, which maps a 3D vector to a D vector, D-dimensional, 2D-dimensional vector given by x plus y, then z. Okay, so I take the sum of the first two vectors, then leave the third one alone. So I have a vector of 2D variables. So the third one, I call it R, and it's two-dimensional. It has two variables, and this is the Euro sum. Okay, this is T and this is R, x plus y. All right. So just to distinguish this different sums, they all related to sum, but in a different way, right? So they act. This guy act on two variables. These two guys act on three variables, but the range of these two guys are different. Maps are different. So so let's do the proof. So we're going to show that these two guys are convolvable. Okay. So for that matter, we would like to show that this R, right? First, this distribution. We have two distributions. We want to show that these two are variable. We use our definition. So R inverse of any compact set intersecting the support of T convolve with S times the support of U. Our goal is to show that this intersection is a compact set. And so let's first bound it from above. Okay, just this set. First observation is that this guy is included in T plus support of S times support of U. Okay, so here I use our property, our proposition 10.10 on the support of the convolution. So we can call this guy star. Okay, so if W is in star, then necessarily it is in R inverse K means that this guy, okay, let me just first look at a second condition, which is this one. if omega belongs to star, it means that it belongs to this set, okay? And which means that x omega or w can be written as this x plus y z with x in the support of t, y in the support of s, z in the support of u. Okay, so this is imposed by this condition in here. So omega belongs to star means that it can be written as such. Also, it belongs to R inverse K means that the sum of its two components in here, each of them belonging to RD, belongs to K. The sum of its two guys belongs to K, and that's by the definition of R. Okay. Hence, we can continue the inclusion. This star is included in T. So T is our map given in here. T applied to S inverse of K intersecting the support of T times the support of S times the support of U. Product space. Okay. Why is that? So this is because for any W belonging to omega, W belonging to star, we have that it is precisely, yes, it is precisely this XYZ such that it is precisely the XYZ which is the inverse of K by the map S, such that first variable of is this W is given by X plus Y, and the second variable is given by Z. The XYZ is taken from here. Okay, so this is good because this guy is compact according to the convolvability condition that we have in here, right? This is compact, and since T is a continuous map, the right-hand side, the whole thing is also compact. And this is what we want to show. We want to show this guy. We want to show this guy is compact. We show that this is included in this guy, which is compact. Okay. All right. So remains to show the formula. It remains to show this formula. Okay, so I claim that it suffices to show it for TSU when TSU are actually C-infinity functions. Okay, so proof of the claim. Suppose that the formula is true for C-infinity functions. Okay, then we can regularize each of the distributions. So I can define this epsilon F epsilon as T convoluted with rho epsilon, where this rho epsilon is approximation of identity, converges to the delta function. And then we know that convolution is a continuous, so that this guy converges to T in distribution. Okay. So similarly, we can define, okay, just to write whole thing at the same time. So we can define G epsilon as S convoluted with rho epsilon, and H epsilon is U convoluted with rho epsilon. Then we have F epsilon, G epsilon, H epsilon converges to T as U in the space of distributions. Okay? This means that each of the component converges to the corresponding component. Okay, so F epsilon, G epsilon convoluted with H epsilon will converge to T as then U. On the other hand, since we have already assumed that this guy, the formula holds for C infinity functions, and we know that this is C infinity functions because rho is C infinity functions, it's good functions. So this guy equals to F epsilon convoluted with G epsilon convoluted with H epsilon. So this guy will converge also to T convoluted with the convolution of S and U. Okay, so necessarily this limit will be equal. So once we have the formula for C infinity functions, then necessarily we have the formula for general distributions, of course, convolvable distributions. So finally, we just consider C infinity functions. Let F, G, H be C infinity functions, which are convolvable, 3 of them. Then this formula, F convoluted with G, then H equals to F convolution of GH. So this can be justified just by Fubini. Okay, so the proof is done. All right, so we are finished with all the basic properties of convolution. So the convolution is a really important topic, and next time we're going to look at a bunch of applications of convolution in the study of some simple PDEs. Okay, see you next time.